Everyone, and welcome to our session today about RDBMS to NoSQL, practical advice from successful migration. My name is Tomer Sandler. I'm a solution architect with ScyllaDB. And today we will be talking to you about RDBMS to NoSQL. With me today is Doug Stans. Doug is a NoSQL migration expert, and I'd like to share a bit more about him for those of you who don't know him. Doug has been working with the latest database technologies for more than 30 years, including both SQL and NoSQL. He has written many books on the Oracle database and has migrated companies across many different industries and use cases from RDBMS to NoSQL. So Doug brings to this discussion an in-depth knowledge set based on real-world experience migrating from RDBMS to NoSQL. Doug, you want to say hi to the audience?
Yep. Thanks for that great introduction, Tomer. Yeah, I've been working with RDBMS and combination of NoSQL migrations and in hybrid formats for quite a while now. And it offers just a great benefit to companies' data service platforms.
Yeah, I just want to mention that during this session, we will be posting some relevant links in the Zoom chat. So you might want to keep an eye on that. Okay, let's move forward. So on the agenda today, we have the following subjects. SQL versus NoSQL basics, how to migrate RDBMS to NoSQL, the hybrid SQL versus NoSQL model, features for full conversion to Scylla, and a little overview about the migration process. So let's start with the basics here. So SQL and NoSQL represent two of the most common types of database. SQL stands for Structured Query Language and is used in the most modern relational database management systems, also known as RDBMS. Relational databases use a rigid structure of tables with columns and rows. There is one entry per row, and each column contains a specific piece of information. The highly organized data requires normalization, which reduces data redundancy and improves reliability. In relational databases, the queries are mostly an afterthought, and the data model is based on the entities. Popular relational databases include IBM DB2, Oracle Database, Microsoft SQL Server, and MySQL. On the other hand, we have the non-relational databases that are often implemented as NoSQL systems. There is no one type of NoSQL database. There are many different schemas, from key value stores to document stores, graph databases, time series, and wide column stores. In NoSQL, you need to consider the application before thinking about the data, as the data modeling is query-based. Some NoSQL systems also support a multi-model schema, meaning they can support more than one data schema internally. This separation of different data stores in contemporary systems can be arcane. There are in the market data stores who cover 2 or 3 of these combinations in one solution. Unlike the ANSI or ISO processes for SQL standard, there is no industry standard around implementing NoSQL system. The exact manner of supporting various NoSQL schemas is up to the software developers. Popular non-relational databases include Apache Cassandra, Apache HBase, MongoDB, Redis, and Scylla. Now let's take a short look into the architectural differences. First of all, the CAP theorem. It explains why a distributed database cannot guarantee both consistency and availability in the face of network partitions. The theorem says an application can guarantee only 2 of the following at the same time. Consistency, the same answer is given to all. Availability, access continues even during a partial system failure. And partition tolerance, operations remain intact even if some nodes can't communicate. While there are 3 elements in the CAP theorem, the trade-off is mostly between 2, availability and consistency. The third element, partition tolerance, is often considered as a requirement for both. A useful compromise is to allow for eventual consistency for the purpose of better scalability. When an application gives up strong consistency, where every copy of the data in the system has to match before the transaction is considered completed, it instead becomes eventually consistent. The decision is based on business consideration. How important is each transaction? For a situation where each write of the data is vital, strong consistency is a requirement. For a situation where the aggregate speed or scale of big data management is more important than the specific correctness of any particular query, eventual consistency might make more sense. Cloud-native applications tend to choose the guarantees of availability and partition tolerance over strong consistency. This is because cloud-native applications usually prefer to keep up with scalability targets than to ensure database nodes are always in communication. Now let's talk a little bit about the ACID and base models. These are models for database design. The ACID model has 4 goals that stands for atomicity. If any part of the transaction isn't executed successfully, the entire operation is rolled back. Consistency ensures that the database remains structurally sound with every transaction. Isolation, transaction occurs independently of each other and the access to the data is moderated. And durability, all transaction results are permanently preserved in the database. Relational databases and some NoSQL databases, the ones that support strong consistency, that meet these 4 goals are considered ACID compliant. Other non-relational NoSQL database, however, turn to the base model to achieve benefits like scale and resiliency. Base stands for basic availability. Data is available most of the time, even during a failure that disrupts part of the data, as the data is replicated and spread across many different storage systems. Soft state, replicas are not consistent all the time. And eventual consistency, data will become consistent at some point in time with no guarantee when. Base principles are less strict than the ACID guarantees. The base model values availability over any other value because base users care most about scalability. Now, let's talk a little bit about the query data structure and consistency. So the structured query language, SQL, is used in relational databases while other interfaces are used in non-relational databases. For example, MongoDB uses a JavaScript query API. NoSQL databases may have their own custom proprietary interfaces, or they may share a common query method. For example, a number of NoSQL databases, including Apache Cassandra, Scylla, DataStax Enterprise, and even cloud-native databases like Microsoft Azure Cosmos DB, supports the Cassandra query language, CQL. While CQL and SQL share many similarities, like database sublanguage and using similar data manipulation statements to store and modify the data, for example, create, alter, drop, truncate commands, a key difference between SQL and CQL is that CQL cannot perform joins against tables like SQL can. The query results are also presented differently. SQL returns data type values, while CQL can return objects. CQL is also massively scalable, designed to query across a horizontally distributed cluster of servers. And as you can see in the table, there are a few more differences or considerations that you should take into account. Now, let's talk a little bit about strong versus eventual consistency and normalization versus denormalization. Consistency refers to a database query returning the same data each time the same request is made. Strong consistency means the latest data is returned, but due to internal consistency method, it may result with higher latency or delays. With eventual consistency, results are less consistent early on, but they are provided much faster with much lower latency. Early results of eventual consistency data queries may not have the most recent update. This is because it takes time for updates to reach the replicas across a database cluster. In strong consistency, data is sent to every replica the moment a query is made. This causes delay because responses to any new request must wait while the replicas are updated. When the data is consistent, the waiting requests are handled in the order they arrived and the cycle repeats itself. SQL database generally supports strong consistency, which makes them useful for transactional data in the banking and financial industries. While SQL-compliant NoSQL databases have tunable consistency, which provides low latency and high write throughput best suited for analytical and time series data. Now, the difference between normalized and denormalized data is the method used for storing and retrieving it. Denormalized data is combined in one table. This speeds up data retrieval because a query doesn't have to search multiple tables to find information as it would in the normalized process. Everything is in one place, but data may be duplicated. The added speed comes at the expense of more data redundancy and less data integrity. On the other hand, normalized data is stored in multiple tables. One type of data is organized in one table, the related data is stored in another table, and then table joins are used to connect relationship between the two tables. The benefits of normalized data includes reduced redundancy, better consistency, and greater data integrity. But the practice can produce slow results, especially when there are complex queries with a lot of data to process. So to conclude, we can say that in normalized data, the emphasis is on faster inserts, deletes, and updates, OLTP, whereas in denormalized data, the emphasis is on faster search and analysis, which is more categorized as OLAP. And with that said, I'll hand it over to Doug to talk more about when we should use SQL versus NoSQL.
Hey, thanks a lot, Tomer. So I'm going to dive into kind of a practical overview on migrating NoSQL to SQL, and some of the key steps you need to, or key differences you need to know right away on whether or not to make that decision, whether or not it makes sense for your organization is when your application requires 100% ACID compliance. That's a use SQL, kind of no-brainer right out of the gates. When you need to go to geo-replication or global and combined with low latency, that's when you use NoSQL. Some other kind of facets along that line are, the relational database model or SQL. It's ideal for handling models that are well understood, may not change often, require adherence to strict standards, typically your COTS-based applications for certain OLTP operations. And then for businesses that value data consistency over transactional speed. So let's move to the next slide. So now we kind of dive in how to migrate your RDBMS. You assume you've determined it's a good solution to move to NoSQL, the whole RDBMS or a piece of it. And one of the main difference or considerations that is opposite of how you deal with an RDBMS is you always start with query patterns from the RDBMS application. So whereas in RDBMS, you may start with a model, right? And you drive that out. So in the NoSQL world, you get the queries. You start with the query patterns. You drive those back to the primary keys in the RDBMS, and you match those out in your NoSQL. A lot of the capabilities are there. Additional indexes can be added. Secondary indexes can be added. We'll go through details of those features in Scylla later, but it's really, just looking at the primary key in the RDBMS, as we give a little example here, and then creating the partition key, which is how that data gets distributed amongst the nodes in the cluster. And it's very key because it organizes that, and that's part of how you get the speed and performance that you may not get in your RDBMS. And then the cluster ordering key for uniqueness, which can be created after that partition key in your CQL create clause. So very close to an RDBMS, but some differences you need to keep track of. Here's an example query here. And then on the next slide, again, how you would do this is you would take your primary key from the RDBMS, you would see, hey, I've also got some unique performance indexes on there. The application may be querying those outside of the primary keys, something to, to make sure that I reproduce in my Scilla NoSQL environment. And then you would just turn that in to the partition key, and the partition key, you got some options. It's important to look at your data so that you don't build oversized partitions. So, you can get more granular with that partition key. In this example, you could use just customer ID, or you could make a compound partition to break up your partition sizes even smaller and get, better performance out of them in smaller partitions. Again, the clustering order key is just, uniqueness added to that partition key. In addition, for performance indexes, Scilla NoSQL provides secondary indexes or materialized views to fulfill application requirements, for performance, different things that you might be running against that data that don't match the partition key and cluster ordering key. And now in the next slide, we'll kind of go through the details of these features. They're not shocking. They've been in RDBMSs for, quite a while, and they operate the same way in Scilla NoSQL. Here's an example of a materialized view, and it is just an inline view that gets physicalized to disk. But for the developers, you can see they can now query below outside of the partition key. And that's really important because without things, you're stuck to go back to fulfill all your queries with a partition key. So, a materialized view is very handy for the application and developers. In the next slide, we'll show the secondary index, which under the hood is implemented as a materialized view. But again, this gives you another way to query the data outside of how it is optimally organized by the partition key around the ring. Next slide, please. So, modeling differences in RDBMS to NoSQL. The main and biggest difference is RI, referential integrity, in RDBMS. Everybody's accustomed to it now. It's been ingrained. You enforce that referential integrity inside the database. In Scilla, the relationship can be made, but it's without the constraints. So there's no RI enforcement at the database tier. It has to be handled up in the API layer to assure that that data exists in the other table it can be, compared against. It's really not that, uncommon, because in the early RDBMS days, there was no RI either. It was all done by a naming convention of the primary to the other table it was related to. So for those of us that have been doing this since pre-RI, it's just like doing a database in pre-RI. And everybody's familiar with, the issues associated with RI and maintenance. You have to walk the tree to clean your tables up, and some cases turn off the RI to do maintenance operations. So, I don't really look at this as a con at all in any way. And let's go to the next slide. So recently, the NoSQL world has now evolved to have some rich modeling tools. Everybody, I think, in the RDBMS world is familiar with Irwin, Toad, Embarcadero. All of these tools have all of these different tools for, third normal form modeling have existed for quite a while. And, there's a kind of business standard to developing these models, get approval, and visualize them. And then from there, generate your physicalization of that database so that it can be implemented. Well, Hackalade is one of the new modeling tools that works for NoSQL, a bunch of variants, Scilla including in there, and it can do the same thing. It can do, you know, all of those kind of things you expect in the Irwin world. And the real nice thing about this is, you know, it really gets the modelers involved in the NoSQL type of work that, you know, maybe didn't exist 5 years ago. Let's go to the next slide. So here's a quick example of what Hackalade looks like. Looks very similar to Irwin. You can see, you know, you've got your column families or tables there, the keys that relate to it, and what have you. I just noticed a question came in on Hackalade. One of the features of Hackalade, it supports reverse engineering and forward engineering. So you can point to a key space or equivalent of a schema in an RDBMS, and you can suck out that CQL or actual commands from that, which is really, really nice because you can get a quick picture that you've kind of come to expect in the RDBMS world. So really excited about this. I only envision more modeling tools to come in the NoSQL world. Let's go to the next slide.
So we have a short poll that we'd like to share with you today to help us better understand your point of view. Let us bring it up. It's only 4 questions, and it would be great if you could spare 1 minute to answer. So you should now be seeing the poll. Let's run through the questions. How many of your workloads are running in RDBMS? Please choose one of the options. Second question is, what percentage of your SQL workloads do you expect to move to NoSQL? And again, you have a few options. Third question, what factors have kept you from moving to NoSQL? Here it's a multiple choice. You can select more than one option. And the last question is, what missing features are keeping you from migrating to NoSQL? Again, it's a multiple choice. Feel free to answer, and we will keep these questions up for another half a minute or so. Okay, I see some answers coming in. That's good. Okay, I still see votes coming in, so we will keep the question for another 30 seconds. Want to give everybody a chance to make a difference. Okay. Okay, so let's move on with the rest of the session. So thank you for your answers on the poll. Doug, I want to bring in the hybrid model into the discussion. Many deployments nowadays are utilizing the best of 2 worlds. And in the current times, the combination of multiple clouds together with hybrid usage of SQL and NoSQL systems is becoming more and more common. Users deploying in microservices are utilizing the right data stores for each of their use cases. So using SQL and NoSQL is not just a black and white decision, right, Doug?
That's really correct. And that's the real trend that we're seeing out there today. You know, some of these RDBMSs, they've been around for a long time now. They're huge. They're maybe developed in the pre-Agile days of Waterfall. They're a big project to move totally, you know, completely and all encompassing. So a lot of companies have pain points in the RDBMS, large growing data areas that can be identified and targeted for a move to NoSQL Scylla type operation. And some of the benefits that this gives you is you may be, being forced in the RDBMS world to really go to some solutions that are very expensive. And, let's just face it, RDBMS, 10 years ago might have been the right choice to store all of your data points. But now, with Scylla and NoSQL options, these could be better to store, your very large IoT data, your very large, growing raw data stream. And then that way you keep your RDBMS right-sized and you're not in this endless loop of changing, your RDBMS enterprise license to support these vast and fast-growing new data sources that exist out there today. Let's go to the next slide. So let's expound upon hybrid and full. So a hybrid migration, as I kind of stated before in a high level, targets those large tables and basically is a much easier project to get your hands around. You're only dealing with the APIs affecting those, the data sources, and whereas a full migration, it targets the whole RDBMS. It can be a more encompassing project, and it has to have really careful thought about the core tables of uniqueness and consistency across the cluster. So I want to drive into those consistency components and how you have to handle those in a NoSQL solution in the next slide. So if you're going to do a full RDBMS solution and migration, at the core of basically every RDBMS is a set of tables that is the primary updatable and immediately consistent core of that RDBMS. It's usually a lot less tables than you think in your whole RDBMS. We kind of grew up in that read consistency at the row level. We're optimizing for that across large clusters that have a shared, everything type situation. So typically when you look at those, it may be a handful of tables. And how we handle that in Scylla NoSQL is with lightweight transactions, which these lightweight transactions are basically based on the Paxos read-ahead transaction approach. And just as it sounds, it's a little more expensive than normal Scylla NoSQL because you have to read ahead, go through a balloting process, and determine uniqueness amongst various nodes in your cluster. So that is an expensive transaction. It's available in Cassandra. It's part of open source, but what Scylla's done is they've reduced some of that overhead by optimizing a couple of the round trip calls and also implementing a pruning mechanism on the system Paxos table. So, sounds complicated, sounds like it's a lot of work to implement. Not really. You just add the if exists to your insert, updates, and deletes, and that forces the read ahead operation to occur. So it's not a big deal. Sounds like, it would be implementing, some complex DR solution in an RDBMS. It isn't. It's just built into the transactional. And we can see right here, just basically, how simple that is. Let's go to the next slide. So you get, you choose to embark on this migration to Scylla NoSQL. And I think this is probably one of the best things about that whole process is the built-in capabilities of the Scylla engine, and the DR and HA is there at its, instantiation of the cluster. It's there for a single cluster, you know, and if we look at the slide up to the right, you have 3 nodes that have complete copies of data. So right out of the gates, you're protected 3 ways for data loss. Well, as you expand upon that with multiple DCs in even one physical data center, it just keeps getting better. Your chance of data even gets fewer and fewer of being lost. It's like winning Powerball, you know, and as you add more DCs, it's like winning 2 Powerballs at the same time. Well, that same benefit also ends up being a total plus in your workflow separation, because as you create more of these DCs, you can do what you can do in complex RDBMS solutions, like distributing workloads on different clusters, read and write, and failover is just baked in. So it just keeps getting better in the Scylla NoSQL world as you start using the base engine capabilities. Maybe you have a customer that's all on the cloud, you know, your base operations are in the, you know, on-prem. So you just basically, you know, add DCs seamlessly to your base database environment. Another thing that is really differentiates Scylla in this NoSQL world is most of these NoSQL solutions that are out there, you scale wide with more nodes. Scylla also adds a new kind of capability that no one else really adds, because the way the software is written and it's very, it's done in C++, they can really scale deep with large nodes that have, you know, 10 terabytes per node, whereas maybe some of their competitors are stuck at, you know, 2 terabytes and 4 terabytes a node. So your choice is this more and more nodes. So the great thing about that is you can have less nodes in your cluster and support huge volumes of data and get still incredible, you know, read write cache hit ratios. So this lowers your total cost of ownership and maintenance. Tomer, you have anything to add to that?
Yeah, I would. So regarding the node density, that's one of the powerful features of Scylla. Basically, we can utilize the very storage intense instances like the i3ENs in AWS EC2, which can go up to 60 terabytes per node. This is something that very few databases in the industry can claim, that they can store 20 and 30 terabytes on a single node. So basically, it's not only migrating to NoSQL and Scylla, and then you can just start deciding not just to keep scaling out like you're used to by adding more and more nodes. You can start scaling up to bigger, stronger instances, which means you can store tens of terabytes on a 3-node cluster or maybe a 6-node cluster. You're going to have much less hardware to maintain. The operational simplicity that you gain by managing 6 nodes versus 60 nodes or 120 nodes, and you still get the high throughput with great performance by all the benefits of Scylla. And of course, you lower the hardware cost, right? Paying for 120 nodes or 300 nodes will for sure not cost as running 6 mega nodes. That's also a great benefit. So I just want to add now a question that I got about Scylla. I got a question, what's the history of Scylla? What company or solo engineer originally created what to become known as Scylla? So basically, Scylla started from the 2 founders, Avi Kiviti, which is Avi is the creator of the KVM hypervisor that was acquired by Red Hat, and then Avi, together with Dor Laor, our CEO, they stayed for a few years with Red Hat, and they moved on to create product called OSV, which was supposed to be an operating system for the cloud. And while they were testing this operating system with various databases that might be able to utilize that, they came across Cassandra, which was a great product in terms of availability and redundancy. But it was written in Java, and there were many issues there about how much data you can store per node and garbage collections and other things that they wanted to solve. And they understood they can basically take the underlying engine of OSV, which is called C star, and utilize that underlying engine to basically rewrite Cassandra from scratch on C++. And that's exactly what we did. And that has been the reincarnation of Scylla. And since then, we've had a lot more. We are fully compatible with Cassandra API. We also have a Dynamo API, almost fully compatible DynamoDB API. And there are other things that we're working on the roadmap, like Redis API. So we keep adding more and more APIs and offerings for Scylla. We started only with the bare metal options, and now we have the cloud options, so you can spin up Scylla as a database, as a service on Scylla Cloud, even on Scylla Cloud, your account, in your AWS account. And you can also spin up Scylla on bare metal, on AWS EC2, Azure, GCP, to manage it yourself as an enterprise. Of course, I should mention Scylla, as Scylla is an open source project, an open source product, but we also have the enterprise offering. So you are welcome to try our open source and also to communicate with us over the user Slack or the Google mailing list for the Scylla community, where we have over 2,000 users. Okay, Now, Doug, I know you wanted to speak a little bit about these ad hoc third-party tools that we can work with.
Definitely, Tomer. So, you know, there's quite a rich abundance of ad hoc third-party tools available. Spark, it's been out there for a while. It, you know, works, it's like a Swiss Army knife. It basically helps with data migrations, data manipulation programs, and just in general, you know, BI capabilities. Presto can do all of the same things, but its real shining point is every organization has a rich abundance of RDBMS developers, and this really jumpstarts the RDBMS developers to use ANSI 92 like query operations to retrieve individual pieces of data for BI, for getting non-partition range lookups that you may not have a secondary index on, and so or a materialized view. So this allows you to just run those basic queries. It's also becoming a middleware layer for lots and lots of the BI tools like Tableau. We can just go down the list, and you can just have those tools that your developers are already familiar with basically connect to the Presto server that is querying your Scylla database. So you don't have to rework all that BI. If your BI is there, there's some optimizations on it, of course, but it doesn't make a complete project rework. You can leverage a lot of things that you already have. Let's go to the next slide.
Okay, so let's talk about the migration process now. This is an interesting issue. So data migrations from RDBMS and NoSQL will require, in some cases, a deep look at the different tables, the table connections, and the way the application is querying the data. So we will divide the migration process based on involvement level. For users who have a complex entity relationship diagram, we will ask you to denormalize the tables. It means that if the application is used to query information from several tables and then join the information to suffice the data query, with NoSQL, users will need to build a table that suffices the query for each one of those queries. It does mean that as a DBA, you will need to interview your developers to understand the data access patterns. In many cases, we have seen that there is a significant redundancy in the application code and underutilized queries. So this is usually something that can be optimized. Once the data model is translated, we will start the actual historical data forklifting. You will be using, in most cases, a transforming tool for your data. The transformation varies between different modes. Some can be a simple export and import of a CSV file. Others will ask you to use a streaming process, such as Kafka, to stream the data from your legacy SQL system into NoSQL. And sometimes there will be no choice and there will be a need for a full data conversion using tools such as Spark to do that conversion. Once the data is absorbed in the NoSQL system, a validation process is required. The teams will verify there is no data missing, as well as that the application is still operating as expected and mostly expected to work better. Validation processes are the longest part of this chain, the migration chain, as you would like to make sure no data is missing or capability is degraded due to the migration. And anything between 2 weeks and 2 months would be a reasonable time frame to conduct the validation phase. To understand the magnitude of work required, I'd like to give you some examples. First, let's think about a key value use case. The key value use case is among the simplest and easiest ones to convert. In this case, there is no true data model, and data conversion and migration is just straightforward. Second, let's think about a key value use case. Think about a document with several attributes entities. It means that there is an attribute we should account for its type and in hierarchy in which it is represented in a table. Last, a complete rewrite of the data model. In this case, you will need to recreate the tables and use the denormalization procedures and best practices to complete the migration. Now, we can help you with these migrations. We do that to help our users and our customers pretty much a lot. So you are welcome to consult with us and to raise your questions and your concerns, either here or over email or any other methods on Slack. And we can help you with the migration process, so you won't have to tackle it on your own. Now, I do see that a question came up just right now about migration. I'll read it out. The question says, what can be done in the validation phase to ensure that the data migration was successful? So going a little bit deeper, during the migration phase, there will be a part of dual writes and reads, including the historical data forklifting. So what you can do after you have the historical data forklifting and you're now doing dual reads and writes to both your legacy NoSQL and your database that you're transitioning to, the NoSQL one, and your legacy database is the RDBMS, of course, you can run various queries to see that everything is intact. You can run a specific query or some complex query, and you can even run range queries or fire up a full-fledged reports that will do something like a full table scan or something that generates the reports from scanning multiple tables and check. Now, usually when there's a lot of data, we're talking about terabytes, you won't be able to go and check every bit of the data. There is a point that you will need to decide, I've verified enough and I'm getting something between, I don't know, 95 and 100% accuracy between the two databases, and I'm good with that. Some customers would like to get to 95% accuracy, and they can live with that. Some customers must have 100% accuracy. So you decide when you did enough validation to declare that you can basically go ahead and flip the switch and make your new Scylla cluster as the source of truth. Now, let me see if we have a few more questions that came in. Some of them we already answered in the chat. Let me reiterate if some people missed that. Somebody asked, when would we want to prefer Scylla over CockroachDB? So we answered that when you need a massive scale, multi-region, multi-cloud, Scylla would be a better solution. And in terms of latency, in most cases, we will be able to provide better user experiences. Another question came up, can a column in NoSQL Word contain a complex structure? Something like the column address that contains location, city, country. So the answer for that is yes. You can use what we call UDT, user-defined types, for creating such a class, such a structure, and use collections, or you can use collections. Probably UDT is the better option for something like address. Okay. Now there was a question also about how SDB is better than MDB. SDB will basically provide an easier scale and throughput per node, while MDB needs to have a lot of auxiliary nodes to scale geographically. SDB will be better to serve data even with a single node, and MDB is a primary secondary architecture. If the master fails, the entire cluster will fail. So data modeling wise, MDB provides you, so data modeling wise, MDB provides a document store, which might be useful in some cases, while SDB provides JSON support. So just a little bit about those differences. Another question that we see coming up a lot by customers or users considering, if I'm using replication factor, let's say replication factor 3 or 4 or sometimes even more, do I still need to use RAID 5 or RAID 10 or any other kind of RAID? So the answer to that is basically no. You can use something higher than RAID 0 by Scylla, but Scylla basically requires you to give it the storage location in a RAID 0 format. Because the replication factor is what will be handling the redundancy and the high availability, okay? If you put other RAID levels on top of it, you will basically just be wasting hardware, and for the architecture of databases like Scylla or Cassandra, that's not needed. Okay?
Yeah, I'd like to just add to that, because these are inexpensive commodity-based computing devices, and if you lose one, you know, you're just going to restream to that. So you typically don't need to deal with any additional parity on the internal disks. And frankly, that just creates more writes and slows things down.
Yep. So another question about, is it a good idea to use Scylla to manage blob objects? And how does blob objects affect Scylla performance? So most of the benchmarks, we show blobs results. So you can find a lot of benchmarks in our website. For example, a very standard tool that we use is Cassandra Stress. So you can use blobs. The only item I would check is the blob size. Do not go crazy with the blob size, as it might affect your performance. But otherwise, there is no problem using blobs with Scylla. So we answered that. We answered that.
There's one, Tomer, on business end users becoming familiar with data available for their particular purpose.
Yeah, do you want to take that?
Yeah, I'll take that. That's effectively those third-party ad hoc tools. That's where Presto really shines, because it's going to allow you, you know, to do a lot of ad hoc analysis on those. You know, you can work with a power user, you know, depending on the expertise that your, you know, business team has, to create some, you know, simple shell scripts that dump data out, you know, and it dumps out nicely to CSV or whatever you want. So, and you can just tie it in with, in a lot of cases, whatever BI tool you're using. So they just query it in the BI tool and, you know, click on a button and create an Excel spreadsheet.
Yeah, okay, thank you, Doug. So let's mark that as answered as well. Currently, I don't see any more questions coming in. There was another question about the create DT field, and Doug answered that, I saw. So Doug, anything else you think our customers should know about? So I can bring up a few examples from our experience in the solution architects team. We have customers that migrated from NoSQL in various verticals, such as the IoT or the entertainment and media. Some of them, you might be getting these links and use cases later on, either in the email summary that will come out with with this session recording. And also in the chat, we have use cases of customers moving from MySQL to Scylla successfully. Some of them to Scylla Enterprise, some of them moved to Scylla Cloud because they wanted the managed service. They didn't, it was a small company. They didn't want to invest in managing their own database. And that's always a good thing. Small companies usually don't have the budget to invest in a full-fledged DevOps team and other teams that might need to handle all the database operational side. So we have Scylla Cloud as an offering, and they migrated there. It was very, very smooth. It was done very quickly. We got great feedbacks. And another example from the entertainment and media is a customer. They didn't migrate from NoSQL, but they had a very bloat deployment of a few hundred nodes, okay? They were reaching the almost 400 nodes with their Cassandra deployment because of some of the Cassandra constraints about how much data you can hold per node, which is usually doesn't go over 2 terabytes. Whereas with Scylla, they basically scaled that down to 70 something or 60 something node. I don't recall the exact number, just by utilizing the architecture of Scylla, where they can store, 15 terabytes per node easily. So that's a huge, huge save. I think they saved a lot. They presented in our last Scylla Summit and had numbers of 6 digits or maybe 7 digits, even almost reaching 7 digits savings on the hardware costs. So that's a huge, huge benefit for us. So you should consider that. Anything else, Doug, you want to add?
No, I see another question came in, Tomer, on somebody saying we are on an Oracle DB. How can I check the DB? And what part of the DBs can be migrated to Scylla DB? Yeah. And so, I would lead down to the point in there of, first checking your referential integrity in the database. And secondly, maybe look at your largest tables that are growing. You can check that by, querying DBA tables or DB. There's a bunch of database, storage utilization scripts. Taking that a step further, if you're running Exadata or ODA, you have to determine, hey, is this database, using, HCC compression on it? Is this a very dense table? Those kind of large tables would, be good candidates depending on, the RI and how they're used with the application on migrating to Scylla. Because anytime you're getting those huge growing tables, those are going to force you to proprietary enterprise type solutions in the RDBMS world.
Yeah. I see here another question about, is it possible to have something like live spaces and archive spaces in Scylla? So I'm assuming they're asking, can they would be able to manage lower price storage and bigger price storage? So what he's basically describing is storage tiering. We still don't have storage tiering as a feature in Scylla, like cold storage, hot storage, etc. But you can have what we call your live data center and your DR data center. They don't have to be the exact same size. You can determine about the replication factor that you want for each data center, for each of your key spaces. So for your live data center, you might want to have it much more available, and you would use replication factor 3 or 4 or more, depends on whatever you want and your hardware availability. But on your disaster recovery or AJ data center, you might use replication factor 1 because that's not going to serve any real-time traffic. And you just want that to be able to run reports on that from time to time, right? Like analytical reports. In that case, you don't need the high availability replication factor. So this is something that you can say about that. And also in terms of, this is in terms of saving money from the storage. In terms of performance, so like this, the faster tier versus the slower tier, we have all kinds of feature in Scila. For example, we have the in-memory tables, which is something means that you can store, you can have a complete table always being served from in-memory. That table would be stored in memory with all the mem tables, but it will also be written to disk. So you'll have that persistent on disk, but the entire table will also reside always on RAM and will not be evicted. So in that case, queries to it, select queries, not inserts, will be served directly from in-memory, which it can get you sometimes latency below 2 milliseconds and sometimes even sub 1 millisecond latencies, like real in-memory databases like Aerospike, etc. Now, generally speaking, Scila has a very good utilization of the RAM and the caching layer. We have what we call the unified caching layer. And in many cases, even without the in-memory tables, if you do the data modeling right, you can have a lot of queries being served from the cache. And by that, you'll be able to achieve very, very low single-digit millisecond latencies. And I'm talking about the 95 and sometimes even the 99 percentile latency. I'm not talking about the 50 percentile. So that's regarding that. And I see here another question, Doug, about how about an analytics package where one doesn't know in advance which of possible 50 fields needs to be the key? Denormalization is great, but not 50x. So right, unless you're planning to have a query for each one of these 50 fields, there is no necessity to do a denormalization on each one of those of these fields. You need to have some knowledge of what you are going to use, okay? But after that, you can, on demand, if you get a request from your developer or from product management that you not need to support some query, you can take that base table that you migrated and start creating materialized view or secondary indexes only on the specific columns that you want to be converted to the partition key. And to that table, you can take some of the others relevant fields. You don't have to take all of them. Okay, you can read more about it in our documentation about materialized view and secondary indexes. So that is also an option for you. And yeah, go ahead.
And I just add there, you know, that's where you might do some basic Presto queries, limit 1, to try to understand your data a little bit and get a general understanding of it to help you build some of those secondary indexes and some of the other things that you may need to do in the database. So again, you know, there's no silver bullet for that. You need to do a little bit of work to understand your data.
Yeah, yeah, exactly. So this is one way to go about that. And if you were talking about the analytics in terms of migration, then you can use a tool like Scila Spark Migrator to basically read all your data from your source database and write it as SQL statements into Scila. That's a very powerful tool. You need, of course, to size the Spark Migrator accordingly. It has its own cluster, and you need to have sufficient workers and all of that and tune it correctly. And we can, of course, help you with that. So we've come to the, it's now 10:59 a.m. PST. We need to wrap up our session. Thank you very much for attending. Thank you, Doug, for joining me today. And we hope to see you all in one of our next sessions. We will follow up, of course, with a follow-up email with the recordings and a few more pointers for you. And you are welcome to join us in our future workshops and webinars. Thank you.
Thank you very much.